So in previous lecture we discussed on moments, expectation, etc. So we have some definition and some theorems on these expectations. So moments, on moments. So this is again on moments, some theorems. This is lecture 8. So we say, it's a definition. We say a random variable x is symmetric about a point x or alpha if this happens. Probability of x greater than or equal to x plus alpha must be equal to probability of x less than or equal to alpha minus x. So these two probabilities is same. So whatever it is, continuous or discrete, this is same for all x. This is for all x. This is also symmetric about. So that means the PDF is actually symmetric, or that probability mass function is symmetric. So the function is symmetric. And now in terms of f, for the distribution function, in terms of distribution function f, what is this? It is just distribution function of x alpha minus x, which is the right hand side, is equal to 1 minus the distribution function at alpha plus x plus the probability of x equal to alpha plus x. That is in terms of f. So, and this is true for all x in real number. That now this is called symmetric, and this point is called symmetric with center. Is also called center. In particular, if it is a continuous type, what happens if f is continuous, then there's distribution function, that PDF f, then f of alpha minus x is equal to f of alpha plus x for all x. So this is the symmetric definition of symmetricity, and alpha is called center. Alpha is called center of symmetry. Center of symmetry. So what is the consequence result? Just a trivial consequence is this. So one result is if x is symmetric, this is symmetric with alpha as center of symmetry, and if this expectation exists, and this expectation exists, that means expectation of mod x is finite, then this expectation of x is actually alpha. So the point of symmetry, the expectation is alpha actually. Now we have some other very trivial results. Is this expectation of ax plus b is just expectation of a into expectation of x into plus b. So if this exists, if expectation of this is finite, so if this exists, then this true. If it does not exist, then no question of equality. Now another result is this: if x is bounded, what do you mean by bounded? The bounded means that is the probability of mod x less than m for some m is 1, for some n, for some positive n. For some positive n, if probability of that is 1, then it's called the random variable is called bounded, and then expectation of x exists. then expectation of x exists. So this is easy. This is, you can easily prove that this is easy. This is trivially true. And the other thing is, if this x is positive random variable, that means the probability of x greater than or equal to 0 is 1, then, and expectation of x exists, this mod of this is finite, then this expectation of x is also positive, or maybe 0. If it's centered at 0, the probability x equal to 0 equal to 1, then expectation of x equal to 0. So this is a very important thing to remember. And next is this: if this is a theorem. So we discussed in the previous class that if x is a random variable, and g is a Borel measurable function, Borel measurable function on R, and say y equal to g of x, then expectation of y, what is the definition? You have a two definition. You have a two thing. One thing, you can just take y as a random variable and take the that distribution of y, and then okay, we consider this as a, say, discrete random variable. We call it, say, okay, we prove for discrete and continuous both. Now, then what happened? Then expectation of x is y is actually somewhere, so y I equal to 1 to infinity, that g of xi into probability of x equal to xi. So this, where this spec of x is just x1, x2, x so this countable set, or maybe finite. This may be finite. Then it is I equal to 1 to n. Now, question: what is the definition? Basically, you consider the expectation of y in two sense. The so you take that x as a random variable, and that we know the probability of x equal to xi. What is the probability of xi? And then product that gxi, and then sum. Another way to define is that, so y is itself is a random variable, and that's why that y itself has, since y is a random variable, this expectation of y is defined in other way. So y has some other spectrum of y is different from spectrum of x, and that probability of x equal y equal to yi. So that means if this is the other definition is this, so the expectation of y, maybe you can define like that: sum over I equal to 1 to infinity, that's some yi into probability of y equal to yi. So yi is at the spec of y1, y2. So it may be finite. One may be finite and one may be infinite. Sorry, if x is finite, then y is finite. If x is infinite, y may be finite. So is this two things are equal? That is the question. And the theorem says yes, these two things are equal. And for again, for this integration thing, for x and y both are continuous, thing. There is a problem if x is continuous and y is discrete. We will not discuss that thing where x is continuous and y is discrete. So if for x and y is continuous, then what happens? Then we have to prove that gx with that fx dx, that must be equal to y hy dy. So what is f? F is the PDF of x, and with h is PDF of y. So that we have to prove that these two are equal. So provided that, obviously, that we provided that g the expectation of mod gx is finite. That is given. Otherwise, is not defined. So provided this is finite, that these two are equal. So how do you prove this? So proof like that. So let first x is a discrete random variable. X is discrete. So first proof for discrete class. Now suppose probability of x equal belongs to a, that is 1. So that is the actually the spectrum. Now if y is equal to gx is a one-to-one map, 1 to is one-to-one mapping of a onto some b onto b, then what happens? So then probability of y equal to y is nothing but, you know, that is the probability of x equal to g inverse y. So it's 1 to 1 for y belongs to that b. Now somewhere gx into probability of x equal to x, that x in a, that is the spectra of x, is equal to that y belongs to b. Since x belongs to a, then y belongs to b, and this gx equal to y actually, and this probability of x equal to probability of y, because it's 1 to 1. And actually it is also true for not only for 1 to 1, it is actually true for it is not many to 1, then also true, because then probability of y equal to y is that you can't write that as a probability of x equal to x. You have to club all these xi's which have give the same y. So you can easily you can just modify the proof for the not 1 to 1 function. Then what is for continuous type? If x is continuous type, f is continuous with PDF f, then whatever, then integration minus infinity to infinity gx fx dx is actually integration. This is a change of variable y, and that f inverse that g f of g f of g inverse x is a g inverse y, f of g inverse y, and ddy of that g inverse y dy, and take the mod value of that. So you know, you already proved that. Now changing that variable y, thus we have this. So this is actually hy. So this is actually hy. So y, this is actually hy. But if g is not 1 1, if this is slightly complicated, if g is you assume that PDFN and g is 1 1. G is not 1 1. For discrete it's easy. For discrete it's a exercise, and for continuous it's slightly hard. So for continuous is hard. So we not prove for the where g is continuous and not 1 1. So this proves that you can consider the expectation of g or x in two different ways. Now next theorem is this: if moments of some order r is exist, if that moment of some order r exists, that means expectation of this exists, then expectation of the lower order, say s, is also exist for 0 s less than r. So for is expectation for higher order exists, then that is lower order exists. And what is the proof of that? So we prove it for the continuous type, and discrete type is similar. Let x be continuous. So, similar proof of the discrete, you have to just replace by the integration by the summation. Then what is the definition of expectation of x, that mod of x s? This is just integration of x mod x to the power s fx dx. F is the PDF of and f is PDF of x. So this is the definition. Now this you can break into two parts. That you can break into two parts. That integration of mod x whole to the power s is less than or equal to 1. And another part is mod of x whole to the power s is greater than strictly greater than. So it's less than or equal to 1, then it is strictly greater than. So we break this in two different parts. Now what is this? This is less than probability of, what is this? This is probability of mod of x whole to the power s less than or equal to 1. So just a probability less than or equal to 1. Plus, what happened? This is less than or equal to 1. Whether it is less than equal to 1 plus this part is actually less than expectation of mod of xt. Why it is so? Because mod of mod of x is whole to the power s, if it is greater than 1, that implies that and t is and r is greater than s, so it is t, not t, it is r, and r is greater than s, then what happens? Then x to the power, this is actually less than, so higher, it is a higher power, so it will be less than. But for x less than mod x less than or equal to 1, that is not true. So okay, so you just take one more line, right? Line that the first part is actually, it is less than or equal to 1, so we just replace by that, and second part we replace by that x to the power r. Now this is equal to actually the probability of, this first part is probability of x to the power mod x to the power less than or equal to 1, and second part you just take the it is minus infinity to infinity, it is less than or equal to x to the power, and that is a expectation. So this is probability of mod x less than or equal to 1 plus the expectation of mod of x. Now this is finite, and this is less than or equal to 1. This probability, so probability is less than or equal to 1. You just write this is 1 plus this. Then just write 1. This is less than or equal to 1, so it is 1 plus expectation of mod x equal to the power r. So this is finite. So if you just add 1, this is also finite. So if expectation of mod x whole to the power r exists, then expectation of mod x whole to the power s also exists for s less than or equal to r. So this is a very important thing, is higher order moment exists and the lower order moment exists. If variance exists, then expectation exists. Actually, obviously the variance is defined in terms of expectation. The second order raw moment exists, then the first order raw moment also exists. Now the next theorem is this. So let x be a random variable. So random variable on the probability space, omega script s and that probability p, and let the expectation of mod x whole to the power k is finite for some k. For some k positive it is finite, then what is true? Then n to the power k probability of mod x greater than n, that tends to 0 as n tends to infinity. So this is very important result, important theorem to prove the next part of the probability, to prove some theorems on the next part of the probability in limit theorems. So again, we just assume that x is continuous, x is continuous, and the discrete part is similar. X is continuous, the discrete part is similar. Now what happened? Now this integration mod x whole to the power k fx dx, this is limit n tends to infinity mod x less than equal to n. So this is minus infinity to infinity, but we take the Cauchy value. Why we take the Cauchy value? Because we know that integration exists. Since the integration exists, that's why we can take the Cauchy value. It may be true that Cauchy value exists, but integration does not exist. But once this integration exists, the import integral exists, the Cauchy value is exists and same. So that's why we take the Cauchy value of this. So we take the only one n, not taking the minus m to n. We are taking just minus n to n. Now this is we know this is finite. So this is finite. So this is less than infinity, because this is we know this is infinite. This is the expectation of mod x to the back, and we assume that is true, that is less than infinity, so it's finite. So this is finite. Now, so what happens? So limit n tends to infinity, that mod of x strictly greater than n, that the complement part now 1 to the power k fx dx, that tends to 0. So this, since this is finite for as n tends to infinity, so the tail part should be goes to 0 as n tends to infinity. The tail part must be 0. So it is like for a sequence, if this is sort of series, if the series is converged, then the tail part must tends to 0. We know that if series is converged, then n tends to 0. So the tail part tends to 0. But what is this? But that greater than n mod x equal to the power k fx dx, it is nothing but greater than equal to x to the n to the power k, because x is greater than n, so it is greater than n to the power k, and this is just a you just take outside and mod x greater than n fx dx. So this is nothing but x to the power n and probability of mod x greater than n. So we get the result. So this completes the proof. Now this is a very important result, and also it is easy result, that is one important result is this. The next important theorem is this: let x be a non-negative random variable. Be a non-negative random variable. What do you mean by non-negative random variable? Non-negative random variable with a distribution function f. So what do you mean by that? So that means the probability of x greater than or equal to 0 is 1. Then it is true that then expectation of x is integration from 0 to infinity. For discrete case, it is similar type. Similar result is true for discrete case. So for continuous, this expectation is nothing but 0 to infinity 1 minus fx dx. That is very interesting. Obviously, it is assumed that they are both this is exist, provided the If one side is exist, then other side is exist. That means so if one side is that if the left hand side does not exist, then the right hand side does not exist. If right hand side does not exist, then left hand side does not exist. If right hand side exists, then left hand side also exists and equal to that. And similarly, if left hand side exists, then right hand side is also exist and equal to this. So if once this one is exist, one of the right hand or left hand, one of this exists, then both again other is exist and equal. That's a thing to say, the equal. And if one does not exist, the other does not exist. So we take the continuous type and assume that proof is like that. So let expectation of x is finite. So we first assume that expectation of x is finite. This is exist. So whatever, then expectation of x is integration from 0 to infinity, because it is positive type, fx dx dfx dx, and this is nothing but limit n tends to infinity 0 to n x fx dx. Now we use the integration by parts. If you use integration by parts, what happens? Limit n tends to infinity by parts, you use that by parts integration. So what is this by parts? So we first take that x and then integration of f. And then its value from 0 to n minus the derivative of x, which is 1, and integration of f is, which is capital X, and this is 0 to 1, 0 to n. Now put x equal to 0, this is 0. Put x equal to n, this gives limit n tends to infinity. This is n fn minus, this is integration 0 to n fx dx. So next it is just limit n tends to infinity. You just take minus n here, minus n plus n fx, and take plus n here. Since it take plus n here, it is just you can take plus 1 minus fn. So integration of fx. Integration of 1 is n. Integration of 1 from 0 to n is n. So this is n. N cancel out, and this is minus of integration of fx. Now this is the limit n tends to infinity. You can write that as minus n into 1 minus fn plus 0 to n 1 minus fx dx. Now, how do you show that right hand side exists? So now n into 1 minus fn. What is this? This is n into integration from n to infinity fx dx, and that is strictly less than integration of n to infinity x fx dx. Just x is greater than n. And since this exists, basically we assume that the expectation exists, so this tends to 0 as n tends to infinity. Since this expectation that improper integral exists, this finite, so that tail part should goes to 0. That means the limit n tends to infinity, that n into 1 minus fn tends to 0. So this part goes to 0. First part goes to 0. What about the second part? that integration 0 to n 1 minus x, and that is we have this we have therefore is therefore expectation of x is nothing but the limit n tends to infinity 0 to n x f x dx, which is nothing but limit n tends to infinity. That first part is 0, so second part is there, so 0 to n 1 minus fx dx. So we prove it. Now you have to prove the other way also. You have to prove the other way also. If now conversely, let that integration from 0 to infinity 1 minus fx dx, that is exist, that is finite. Then what happens? Then integration from 0 to n x fx dx, that is less than or equal to integration of n integration of 0 to n 1 minus, we already prove it, that is less than this, and this is less than equal to 0 to infinity 1 minus fx dx. We have to prove it that this is less than equal to 1 0 to n. Similar way. Now this right hand side, this is finite. So since this is finite, we assume that therefore this is finite. That means 0 to n x fx dx. This is finite for all x or all n. Oh no, you can't say this is only finite. You actually say this is since this is true, then this is true for all n. Then that means the limit n tends to infinity also exists, and that is less than or equal to that part. So that means this, therefore, this expectation of x exists. But the question is why they are equal, and that proof is slightly tough. I just leave. So that part is tough. So to show, now we have to show. Now we have to show this expectation is actually equal to this 0 to infinity 1 minus fx dx, and that is hard. So we just omit this proof. It's hard. This proof is hard, and we omit this proof. So that means for the non-negative random variable, the finding expectation is easy in sense of you just have to integrate from 0 to infinity 1 minus fx dx. And that result is actually useful for to find some expectation for some distribution, which is non-negative distribution. We already defined for variance, and we know what are the different result for the variance. The different result for the variance is like that. If x is variance of x is 0, if and only if for the variance the results are this. If variance of x is 0, if and only if it is degenerated. So that means there exists some c in real numbers such that s probability of x equal to c is 1. Next, we know the variance of x is less than, we know the variance is less than for the other value of this for any c not equal to expectation of x. So it is least, the variance is the least among the all, sorry, this is square, least square thing. And we know this also thing that variance of ax plus b is nothing but the s square variance of x. That left as exercise, you know this. One more thing is, if you take z as x minus expectation of x by root over variance of x, assume that the variance and expectation exist. We sometimes write that is mu, and this is called sigma standard deviation. Then what happens? Then expectation of z is 0 and variance of z is 1. So this is called standardized variable random variable. This expectation is 0 and variance is 1, then it's called standard. It is standardized. If I say what is a standardized random variable correspond to the x, that means x minus mu by sigma. It is standardized random variable. So x is called the standardized random variable. Now next thing is you have to find all these moments variance for the binomial for Cauchy, that is left as exercise. Different distribution, finite or discrete or and continuous type. You have to find that all the moments, and these are all left as exercise. Next thing is generating function. Is very important thing. Generating function. What is the generating function? There are different generating functions like characteristic function, moment generating function, probability generating function, etc. So what is the generating function? So generating function, so first the probability generating function, PGF, the probability generating function. What is probability generating function? This is for only discrete type. This is for only discrete type. The probability generating function for a discrete type random variable x is discrete. So remember that probability generating function for the discrete type random variables. Then the probability generating function is say P. The P is a generating function, probability generating function. The PS is actually sum over that s to the power k into probability of x equal to k. Oh, by the way, this discrete random variable with you have to take the spec with spec of x is just 0, 1, 2, that all non-negative integers. If it is all non-negative integers, then we define, then only we can define. If random variable with non-negative integer value, then we define the probability generating function like x ps is like s to the power k into probability of x equal to k, and for k from 0 to infinity. If it is finite, no problem, you just take k from 0 to n or from 5 to n. If it is say only 5 from 5 to 10, so then k is from 5 to 10. And again, you have to find the probability generating function for your that Poisson random variable, your binomial random variables, and Bernoulli, etc. hypergeometric. That is left as exercise. You have to find the all this probability generating function for the discrete type random variable with non-negative spectrum. So the spectrum as a non-negative integers, and eventually all this distribution in our syllabus, that is negative binomial and hypergeometric, all these things basically non-negative random variable. So that's why you can always find this probability generating function of this. So that left as exercise. Then the definition is the moment generating function, that MGF moment generating function. So definition of moment generating function is this. Again, x is random variable. Now you can take x as any it is continuous or discrete. Now moment generating function defined like that. M of s is just expectation of e to the power sx. For discrete it is summation, and for continuous it is integration for all s in real number. So this is defined for all real number. So again, you have to find all this. One thing, this is you have to take that for probability generating function for you can't take all, because to convergent you have to take for all s less than mod s less than 1, less than equal to 1. You have to take such s that mod x less than equal to 1. You can't take all s. This is a question of convergency. So if s is mod x less than equal to 1, then it's converge. Otherwise, it may not converge. So moment generating function you can take any s for all s. Now again, you have to find this all moment generating function for all this whatever in our syllabus, that continuous, discrete, that Cauchy, binomial, Poisson, normal, whatever, you have to find this moment generating function that is left as an exercise. And this important result for this moment generating function is this: if this m is the moment generating function for x, and if it may not exist actually, that if ms is exist for s in minus s0 to s0. By the way, this may not exist actually. This moment generating function may not exist. Actually, we have to take such a all x where this expectation exists. That we have to take that x for which this exists. Now, MSS exists for this thing. If this exists in minus s0 to s0 for some s0 positive, and the derivative of the order at all order exists at s equal to 0. So, and the derivative, and we assume that the derivative, all order derivative, that derivative of all order derivative is called smooth function. If it is smooth at a 0, so it is all order derivative of all order exist at s equal to 0. So may not be exist in all value, that exists around 0. So it is smooth around s equal to 0. If this function is that's function m is such a function that derivative is exists for all order derivative exists for s equal to 0, then what happens? Then m to the power that the kth order derivative, this is called the kth order derivative of that function at s equal to 0, is nothing but expectation of x to the power k for all k natural numbers. So this is very important reason. That's why it's called moment generating function. This, if you know the am, then the kth order derivative at s equal to 0, this actually expectation of the raw moment of kth order raw moment of x. And actually you can find it by the Taylor series expansion. So it is using Taylor series expansion, Taylor-Maclaurin series. You can just write ms as your m0. You know this is all this order exists. Then Taylor-Maclaurin series, say it is ms is m0, then m dash 0 by factorial 1. It is like e to the power series or any other series. Like in the Taylor-Maclaurin series, is in second order derivative at 0, then factorial 2, and so on and so forth. Oh, sorry, this is an s is there, and this is s square is there, and so on and so forth. This series is called Taylor-Maclaurin series, and this ms, if all order 0 around 0, all order derivative exists around 0, then this Taylor-Maclaurin series is actually equal to the function around that s for all s belongs to that minus s. It may not be true equal for any s. It is true just for the around 0 small, and we know that that the derivative is just that moment into that divided by the factorial part. That is the coefficient actually. So that's why if you don't know the moment generating function, you can easily find all the moments. So that's why you find the moment generating function, and this is left for an exercise, left as an exercise, that you have to find all the moment generating function for your known distribution. So this is up to for this up to this for in this lecture. Next lecture we just discuss on there are other moment generating function also, like a characteristic function is on one generating function, important generating function, characteristic function, and one is called cumulant. That is not so important, but characteristic generating function is important. That's why, because this moment generating function may not exist for all s, but characteristic function is always exist for exists for all s. But the problem is for characteristic function, you have to know the complex analysis. You need complex analysis. Up to moment generating function, we use that real analysis in that real improper integral. But for characteristic function, you need that complex integration, all this analytic function and all these things in complex analysis. So we leave that characteristic function because complex analysis part is not included in our syllabus. That's why we left this characteristic part. We just find some characteristic function of some standard distribution, but we not go into details into discuss on the characteristic function. The next thing is we need some inequality. That is called moments inequality, some Chebyshev or Markov inequality. This in the next class, up to this in this lecture.